And if you think this is disorganized, you should see me coding. So, let's go. All right. This started off as a bad idea for a workshop that I gave in London in the summer. And it was supposed to be an hour-and-a-half workshop, and it sort of overran by getting on for an hour. So I've taken out the bit that I thought was the bit that people didn't know, and I've put it in this, and it will hopefully fit in a keynote. But if I run out of time, stop me. It's not always easy, but do it. Also, I had sort of wanted something. I'm going to give a big disclaimer up front. I'd sort of wanted to put something truly mad in here. I wanted to show a Y Combinator in Go. And I've got a working Y Combinator in Go. But at 2 o'clock this morning, I could not be asked to paste it up in slides. So at some point, I'm going to put the code from this talk online in my GitHub, probably, or somewhere. And it will have a working Y Combinator as well, which you can figure out for yourselves. And then I don't have to try and explain something that's truly insane. So let's start. Okay, so Go is approaching its 10th anniversary, which means I'm approaching 10 years of inflicting Go on audiences, which is kind of scary, because when I started doing it, I thought, oh, I'll get like a year out of that. Whoops. Oh, what the heck. I don't like being up there anyway. I'm not really at the front sort of speaker. So a few of you may have run across my book on Go. I promise this thing here, honestly. Everybody else will write more than one book. I promise I'll never write more than one book. So buy a copy. It's cheap, and you never have to buy another copy. I just add to it every time I think of something. And this is taken out of a chapter that I'm working on, well, 3 or 4 chapters I'm working on functional programming in Go. I don't like functional programming. I'm not a functional programmer. It's a mad thing for me to be doing, but it's fascinating stuff. And I think the best thing I've ever seen to sum up what functional programming is, a friend of mine, Mike Feathers, he says, OO makes things understandable by encapsulating them. We know what a car is, and we know what a wheel on a car is, and if a wheel turns, we understand the turning of a wheel on a car, and then we understand a car moves. Functional programming tries to remove all the moving parts that you might have to think about a car moving. So a car just moves from A to B, and we don't care about the engine unless we're building an engine for a car, and then we care that it does something. And so this whole talk is about the idea that we're going to use functions, and only functions, to do stuff. Right. So, let me first of all introduce you to the idea of a pure function. This is the thing that functional programming heads start off with. So I thought I'd start there. A pure function is a function that takes 2 parameters, and for those 2 parameters, or 1 parameter, or 3 parameters, or however many parameters, in this case 2, it'll do a certain task, and it will always give the same answer for the same parameters. It will not change anything. It has no side effects. It's effectively like if I have a bag of marbles is a function. If I always say that when I put my hand in wearing a certain glove, the same colored marble will come out, that is a pure function. It's that simple. It's a mapping. Everything you can do with functions, you can do with maps. So you could take all the code I'm going to show today with functions, and instead you could write it as hash maps. And that's really weird, but fast. And we'll get onto that towards the end of the talk. So in this case, I'm going to have this thing that's going to give me it's a command line tool. I like writing command line tools. And I'm going to use the structure of a command line tool throughout this talk. In this case, my command line tool is just going to exit with an exit code. So on a Unix box, this can't give an answer more than 255. Very important to remember that. And it's just going to add together 3 and 4, in this case, and give me 7. I'm not going to show the output because it's kind of like not very interesting. My function takes 2 parameters, returns a result. Nothing outside of that function is being affected. Pure function. So let's get past that. Boom. Right, and we're going to need some boilerplate so that I can take parameters. So I'm going to use string-conv to just basically convert text straight off of the command line. There is no error handling here. It will go bang if you don't give it 2 parameters. It will go bang if you give it... Actually, no, it'll go bang if you don't give it 2 parameters. But if you give it 3, it'll just ignore the last one. So, I don't like doing this early. We can abstract some of that out. Good programming practice is always to abstract anyway. We should try and be dry. Never have code turn up in two separate places if you can possibly avoid it. And as a not entirely recovered Rubyist, I will make code as dry as I possibly can at every possible opportunity. So this function here, arg, this is not a pure function, or is it? It is, because stringcov is just taking in a value off the command line. Now, you could argue it's not a pure function in the sense that it's not taking a parameter there. And I'm sort of implicitly using a parameter. I should really put a parameter there that's whatever the string off the command line is to be a pure function. You could argue that this is a monad, but we're not going to talk about that because I don't care about functional programming theory. I don't think it will help us. But all that a monad is something that hides the fact that state changes from pure functions. So you can have side effects. We're not going to talk about that. There's some very good talks online that will baffle your brain and leave you no wiser. So, obviously, we can use a function again and again and again, so I can range through everything that comes off the command line and I can add it together. So we're going to build something later that's an accumulator. And we're going to look at how you accumulate in a functional program. I'm bored with this example. These early ones are really just to sort of set the scene. So over here, I can abstract out this concept of accumulating. If I want, I can have a global variable that I can use to store up values in here. And this is horrible. This is not a pure function. This function here is interfering with global state, and this is a bad thing. It makes programs very hard to reason about. So we're going to look at how we can get around that in a minute. How we can do the same sort of thing, but not actually do it with global state. So skip past that. Now, boom, 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 boom. We can, of course, have an accumulator as a type. And the advantage of having a type is that we can have a method. And now we're doing a bit of OO encapsulation. But we're doing it, what we're really doing is hiding functions as an object. And we'll get onto that in a little while. So skip past that. Oh, God. There's a lot of slides to go through. OK, skip past that. All right. The interesting thing, functions are something that as programmers we take for granted. They're actually the building block of every program you'll ever write, unless you're using BASIC from the early 1980s and you don't actually have the ability to declare a function. And even then you have GoSub and return, and you're effectively just rolling your own function by putting parameters in a stack or a list or something, or an array or something. Functions are what programming is about. So it stands to reason that we can replace all kinds of things with functions that normally we think of as completely separate ideas. We normally think of a variable not in terms of a function, but in terms of a memory location. And a variable is a memory location at times. I mean, in Go, we have two particular places that variables live. I'm probably going to deviate from these slides a bit. I'm sorry. I feel in the rambling mood, and I want to go into something that's more machine level. So when I'm storing a value, and I'm only going to use it in a chain of function calls, that just gets stored on the stack. It does actually have a memory address, but in Go, I can't necessarily get at that memory address. We have something called escape analysis to try and keep as much of that stuff on the stack as possible anyway. But if I decide that I'm going to go off and I'm going to do something, I'm going to store it somewhere and I'm going to do something parallel to it, I'm going to end up storing it in the heap, which is just a big chunk of memory that lives at known addresses. So I've already got this idea that actually a variable isn't as simple as just a memory address. Sometimes it's a sequence in which things have been declared. And once I'm out of scope, I'll lose it. So in this case, I can decide to effectively, my memory location here is binding off to a function. I'm going to say, you know what, instead of actually having a piece of memory storage, I'm going to have a function that every time I want to access that thing, that function is going to do something for me and give me a result instead. And down here, it's quite simple. This function is going to return a function. One of the lovely things about Go compared to C programming or C++ programming or Java programming until think Java 11, is that in Go, functions are first-class values. I can pass them in as data to things, where instead of it being called when I make the function call, it just gets the function. But also I can return functions as values from things, and I can pass them around. Now that's a pretty neat trick to start with. Many languages have decided to implement that over the years. But what's cooler is that Go goes slightly further than that. It doesn't just implement that I can return a function. It actually implements that I can return an instance of a function. And this is called a closure. A closure is basically just I've defined a function, and when I return a closure, I'm returning a particular instance of that function in which all the variables inside that function and all the state inside that function has been declared. And now as I pass that function around, it moves all that information with it. So in this case, this function I'm going to return, I'm about to do something a bit sneaky. I'm going to declare this variable here in makeAccumulator, and each time makeAccumulator is called, that variable y is a new variable, right? A new memory location for that. And when I return this function knows about that y. Literally nothing else in the program does. So I've now got a private global variable that's private to a single instance of the function. And every time I call that function, I can muck with that variable, but only by calling the function. So I've still got state, but nothing. It's like having a little black hole, pocket black hole that only I can look in. Oh, 53. Add some more beans. 57. You want some beans? Well, I can give you some beans, but you can't put your hand in there to get them yourself. You can't. It's a black hole. Can't get in. Nothing there. So I use this trick a lot. I love this trick. It's brilliant just being able to hide off a piece of global state and being able to do it. And then I can have 3 or 4 different instances of that function running, each running off of their own private state. So now I can have 3 or 4 different things that all operate the same way, but different preconditions, different idea of what the state of the universe is. This is particularly handy when you're doing concurrent programming, because obviously in Go, every time you start a Go routine, you're actually starting a separate thread of execution with a closure. And in most functional programming languages, people would go, that's insane. You've got shared state. Well, yeah, you have got shared state. But the thing is, you can control what that shared state is with little tricks like this. So let's get past that. Oh, God. And of course, obviously, if I define a type for a particular kind of function signature, then I can declare things in terms of that. That's kind of boring. OK, functions as objects. Way. Oh, lots of people do stuff about this. I'm not sure I really want to talk about it. OK, let's go. All right, so I've got my function type, and I can put methods on a function type. So anytime that I use this type signature here, or in any situation where Go would automatically treat a function of int to int as being assignable to this type signature here, I can now effectively force it to be this, and I get an add method. So now my function hasn't just got private state from the fact that I can hide off values in a closure. My private state can now be manipulated perfectly reasonably using selectors and method calls. So now I've got objects with private universes in them, which is kind of neat. And obviously we can do stuff over here where we can, in this particular case, we can take a value in and we can decide what to do. Because I decided to do this because if I pass in an accumulator, it'd be nice to get the value out of the accumulator and add it to what I've got in my current accumulator. But obviously most people, most of the time, are going to pass in an int. So, and I like in Go using interfaces a lot more than I should. Blank interfaces are really handy if you want to have a fairly open and permissive API that will take several different things that all make logical sense to you as the person who's writing it. Please document it if they don't make logical sense to you. But at the same time, make it a lot friendlier to write more generic code. So, right, so what we've talked about there is mostly functions in programming languages. The pure function at the start, that was a function as mathematics understands it, but no reason why maths understands it. So in mathematics, we're used to seeing functions looking like this. There's a big chunk of my late teens and early 20s that was lost to thick textbooks full of this stuff. Not normally this simple, normally horrible calculus stuff, because I did applied physics. And you don't have to be good at math to do applied physics, because it's like we'll keep bashing the balls together and the theoretical physicist will then come and do something with equations later. But B, you still have to actually be able to pretend on stage, if you do that kind of work, and fake it when you're talking about your paper results, that you understand the math. So I can fake everything up to partial differential equations really well, and beyond that it was just like, honestly, I have no idea why these answers turn out the way they do. It's like so many special cases. But in this particular case, this is a factorial function. Whoops. And if I can move back, further away from that I get, the happier I am. That's really a portion of my life I didn't enjoy. I'm out of target range now. There we are. All right, so this first one up here, all this is basically saying is, for any value of x as a parameter, the answer of a factorial is that times f applied to 1 less than it. Or 1. And this one down here just defines this as a product, that multiplication up there defined as a product operator. So it looks like horrible stuff, but it doesn't really have to be. This is the great thing about factorials. They do this. They're insane. So an exponential, which everybody is scared of, goes over there. Factorial just goes, you. Straight off the screen. But they happen to be really, really useful as examples of how to write programs with functions because of the fact they're recursive, and we'll get on to recursion in a minute. So, to start off with, all of the really old, boring methods of solving factorials all involve iteration. That is, I do a step, I check whether I finished, and I do a step again, and I have an explicit loop for doing that. Right? And you'll see this for other problems, like sieve Eratosthenes for finding prime numbers and things like that. They're all iterative methods. And there's a whole branch of mathematics that's just about iterative methods, which was a really tedious 3 months course when I was like 19. Mathematicians will formalize anything, incidentally. No matter how dull and no matter how obvious, they will find a way of writing a 500-page book formalizing it. And that's really a very strange thing. Very opposite to the programmer mindset. We want as little code as possible. In this particular example, we're going to start off. We've got a factorial function, and it's got our special cases. Now, there is no factorial defined below 0. If you pass 0 in as your parameter, the answer is 1, because the factorial is actually the number of combinations that you can have from a set of this many items, which is why 0 gives you 1. You get 1 combination, which is 0. There are 0 things in the set. And it's one of the breaking cases of set theory, which is one of the things that functional programmers base a lot of their theory on things that derive from set theory. So it's kind of interesting. I like to just do in command line things, panic if things go wrong, because it's easiest to figure out what I've done by going, I panicked, recovering from that. So we've got to recover up there. When it's 0, we will return 1. The rest of the time, we start off with a value of 1, and we iterate through and keep multiplying until we've hit our parameter. Very dull. I always do countdown loops for this sort of thing. They're slightly faster in machine terms. Even on modern hardware, nobody seems to optimize for count-up loops in hardware. I don't know why. Which is why none of my talks ever end up not having hardware discussion. And we can simplify that code like that. So, and then we can simplify it further, like that. Yeah. Obviously, when we call the factorial, we'll end up with a value that goes into our printf. And there's not really a lot I want to say about that. I mean, it's a loop. And loops are something that if we're programming in functions, we want to get rid of. Because loops are explicitly not functions. Loops are explicitly a different concept, a process, a series of steps that's followed. Whereas a function is a black box that gives me the right answer for the right parameter. Okay. Now, I'm not quite sure how to describe this particular little digression here, but let's say we want to do several of them at the same time. I want to pass in several different numbers on the command line. I want to calculate the factorial of each of them and print it out. And so off I go and I do my loop, and I've got a panic, and my panic goes to up here. The trouble is this doesn't actually do what I really want to do. What I want to do in my program is, whenever I've got a parameter passed to on the command line that won't produce a factorial, I want to print out no factorial. But this program will only spot the first one, print out no factorial, and then exit. Which isn't what I want to do at all, because it's broken me out of my loop, and I'm not getting back into the loop, and I'm leaving the program. And so I could have 15 different parameters, the first one of which has no factorial, it's -1, and all the others are perfectly valid for giving me a factorial. And I'd really like all of those to print out in the one program, because I'm lazy. So, how do we solve that? We introduced a concept called higher order functions. Now, a higher order function is a function that takes a function as a parameter. And then it goes and it does something to gets the value from that function, and then uses that along with other parameters to give you the result you're after. And so we can rewrite our program subtly differently and now do exactly what I want to do, which is print out no factorial each time I run into a parameter that won't give a factorial. God, I'm not looking forward to watching this back on video. I hate doing morning talks. All right, we've still got our loop, and we're still going to range through all of the available command line arguments. Okay? But now, inside that loop, each time we're going to call a function. And of course, another great thing about Go is we can create inline functions whenever we want to. So in this case, I'm creating this function here that takes no parameters and calling it. This is a closure over that. Whatever value happens to be v when this is called, this knows about. Each step through, it knows about a different v, because each step through, it's a different instance of a function that's being created and then being called. This is a really useful thing to wrap your Go routine launchers in, because one of the most annoying bugs to fix when you write a Go routine that's going to launch, well, when you're going to launch off several Go routines off of a set of values, say out of a slice or something, is as you are iterating through, you will find that Go routines launch so slowly that by the time they've all launched, they've all got the same value as the end of the list, unless the list is several thousand elements long. Because the for loop will go so much faster than the Go routines launch. And I never make that mistake anymore, because I once spent an entire week pulling my hair out trying to figure out where the bug in my program was, and that was the bug in my program. And it's the one thing that you look at it, and the code looks perfectly sane. But by introducing closure wrappers, suddenly things behave differently. Now you've effectively bounded execution within this context. If I now panic in here, well, this panic gets picked up by this defer. But guess what? It just finishes execution of that. It doesn't finish execution of main. So now I can go round and round and round, and I'll get all of the right no factorial or factorial result answers coming out. I can generalize that concept. So I can introduce this idea of a safe executor. It's poorly named, but it's kind of like these examples are always difficult to give good names for things, because it's like, it's not a 20,000 line program I'm going to have to maintain for years. It's more like a 50 line program that shows the idea. Safe execute is an awful name, but what safe execute is going to do is it's going to give me a function that takes a string as a parameter. I'm sure I had a good reason why I wanted to use a string at the time I wrote it. I'm not really that interested in what the parameter type is. In here, I'm going to create this function, and I'm going to give it the recover with the defer. Did I decide to give any of that? Oh, I didn't. And then down here, I'm going to do the actual job I want to do. which is convert. Oh, yes, that's it, because I get to move all the boilerplate for converting that to a number as well. So I'll convert it to a number, and also I can panic if it's not a number, which is quite nice. So I've now got two ways I can bail out, and only one of them will print no defined value for. The other one should probably do something like that, but I didn't really care about the error case in this example. Now when I pass in this function here, every single time that this runs, it'll do me the conversion, give me an integer, pass it as a parameter into that, and then I can print whatever the factorial of that number is. More and more functions all the way down. Effectively, this is how you write DSLs in Go. So if any of you come from languages where domain-specific languages are a popular trick, like they are in Ruby, one of the most frustrating things about first getting to grips with Go is how the hell do I write DSLs? This is how you write DSLs. It's just functions all the way down. So, and obviously our factorial is boring. Now we can do a few other things. I mean, obviously, this is taking a parameter that's a function. So if I want to, I can create a function literal somewhere. I can pass that into my method or function, and then I can say, please use this as the payload. Because now I've split apart this concept of safe execution, completely split it away from what safe execution is about. And in this case, I've also chosen to add in an errors variable. So I can count up errors as I'm going, and then at the end, I can give an exit status, which is the number of errors. How many of those items were erroneous? How many didn't have factorials? So that's kind of nice, because now I've got sort of something completely tangential to the concern of calculating factorials that I can do quite elegantly without mucking up any of the code for doing the factorial. But if I did it inline, the code would be really ugly, and I'd have this mutable remote state that would be bound into it. So skip past that. I'm sure there's a reason why I decided to belabor the point. Oh, yes. I remember now. So the great thing about higher order functions is we can take more than one function as a parameter of a function, because any parameter to a function can be a function. So in this case, I've now split off the entire error handling concept for when we've got no factorial. And I can change that, or I can change that. I can have a different payload. I can have the same error handler. I can have the same payload. I can have two different error handlers in two different calls. And it's nice and easy to do, and it's very clean to do. And there are lots of languages that are not popular with functional programmers who can do it. It's just, you see this stuff normally written in Haskell, and it's like line noise. It's like, no one's getting into that. Now, once you realize that functions can be parameters, you then start to look at, well, if a function can be a parameter, I can do something with that concept. And a guy called Haskell Curry, after whom Haskell is named, but he's not responsible for Haskell. Haskell fanboys are responsible for Haskell. And you can take that in either Haskell Curry fanboys or Haskell fanboys, depending on which community you've run into first. This function call here, f, takes x and y as parameters. That is actually equivalent to calling a function that takes x as a parameter that returns a function that takes y as a parameter. If you happen to be using mathematical pure functions. Trust me, you can write functions in Go that do not obey the currying rule. I don't recommend it because it makes them difficult to think about. But the currying rule means that if I have a function that obeys the normal rules of mathematical functions, it's a pair of bags that you take answers out of, right? Then I can sequence them like this as a set of separate function calls, known as an application in the jargon. So down here, adding x and y is equivalent to having an add function that takes an x, that returns something that can then take a y. And the place to learn about all this stuff properly is to go and read old books on Lisp. Books on Lisp from the 60s and 70s, before Lisp got really taken over by people who weren't programmers. Because all the old books on Lisp cover all of this really nicely. And down here, if I want to do a multiplication, I can do multiplication of x by y by z. I'm multiplying three things together. And that's just three instances of a function that takes a single parameter. So we can do that in Go, as long as we're well behaved. So firstly, I'm going to define this thing on panic for On panic for such and such, run this error handler, which is kind of like tidying up safe execute with a word that makes more sense to me. And in this case, I'm going to give it one function, use numeric param, which is going to do the whole job of getting me a numeric parameter off the command line, and is going to panic if that goes wrong, and that panic is not going to be handled on panic for, right? So on panic for probably needs another parameter to tell me what it should panic for. But anyway, that's by the by. So this function takes this function, and it also takes this function, print error message, which when that there panics, will print the error message. There we are, up there. Notice how we end up with lots and lots of nesting. I use a lot of nesting because it makes it easier to tell which context you're in. Don't go too mad. Lisp books do it with lots and lots of parentheses as well, so you can count the parentheses and So we've got the on panic for, we've got that bit. Oh, coming back. Now the thing is, for this to work, because it's going to return a function, we have to call it. This always involves a function call. We can write it using currying. In a currying world, I would say, oh, by the way, on a panic, here's an error handler. I'll give you back a function that takes a function as a parameter. So anywhere you want to use this to get my error message, my error handler run, just pass in your function inside this function that takes a function as a parameter, right? But it's important, if you want this to really work generically, it's best if this function call here takes no parameters itself, because otherwise you end up having to define lots of these things. There's no real reason to have parameters to functions unless you really need them, because of the way that closures work. So, as a result, we've now got a function main in which a loop is going to call onPanic whenever to tell us how to do a handler for that, inside which we're then going to use numeric param function that's going to take a workload that we want to do, and is also going to take a string which it's going to get from here, that v there. And then this workload here is going to call factorial. So we've now got a stack that's got four, whatever number. I don't do math this early in the morning. Right. We're going to have a stack with this many levels of execution on it. The reason this stuff was not, the reason that Lisp fell out of favor in the very first time round was because you end up with very big stacks. And computers back then didn't have very big stacks. Many of them had hardware stack limitations. Even if you had a megabyte of memory and were like the biggest memory machine on the planet, you might still only have a 32K stack if you were lucky. And this uses up choose stack. We don't have to worry about that. Modern hardware does not care how big your stack is. If you've got 16 gigabytes of RAM, you can probably have about 15 gigabytes of stack. You know, and most of these things are like 64, 128. Maybe we're using about 256 bytes per invocation. So inside 15 gig, that's an awful lot of depth of stack you could have. So anyway, and obviously, of course, we can, as onPanic always is going to give us the same thing, we can optimize this program, slightly. Because here, every single run through this loop, we're creating a new instance of onPanic, a new instance of a function. And we don't really need to do that for what we're doing. For what we're doing, we only need one instance of that. So we can actually create that outside the loop and then call it inside the loop, because it's a function, with our workload each time. So I hope you're starting to see why it is possible to program just with functions, and also how you can actually have some programs that are quite nice to read if you program with just functions, if you name things nicely. I can't stress that point. We're going to have to go fast because, yes. Okay, recursion. The simplest recursive program in Go is this one. Main calls itself. It isn't a good idea, to put it mildly. You don't have enough stack for that, because no one does. The universe doesn't. There is no way that this is stack bounded. It's going to go forever and ever trying to create new stack frames. And so it will go bang. And you'd think that this might help, right? Because I've got to defer, and when I run out of stack, surely my defer routine is going to be able to handle the error. No, because out of memory errors don't get handled by recover. Because recover has to create a new stack frame to be able to do its job, and you have no memory. It's worth going and doing a read on how, there's a good blog post on how Linux handles out-of-memory errors and how it manages what it does with its resources to get rid of things, and the non-deterministic sense of that is quite funny. So we can do something a little bit similar, though. Firstly, init, very useful little function. An init routine, you can have as many of these as you like across your package. They run in non-defined order, so don't put anything in there that's order dependent. But you can set up state in an init, and I like showing off init because not enough people use init. It's possible that living in London and dealing with a lot of people with that accent, that I might think that that's a little bit more fun than it is. I'm going to set up a global variable, a limit. And I'm going to give that limit on the command line. And actually, this is a fun little interactive program you can run to find out what is the maximum number of recursions you can ever perform in a Go program on any particular machine is, by guessing. And then you use a divide and conquer strategy where each time you go for the midpoint of your last guess and your current guess and recurse up and down, and like 20 or 30 guesses in, you'll find out exactly how much memory you can get away with abusing with recursive calls. Minus the little bit of boilerplate, obviously, for the limit variable, which means it's slightly wrong. And in main, I'm just going to keep decrementing that limit in each subsequent call of main. And while that limit is greater than 0, I'm going to try and call main. Right? And eventually, my machine's going to go bang, and I'm going to try another parameter, and so forth. You can write a bash script to automate it as well. That's quite good fun. We can use recursion in sensible and practical ways. Anybody who isn't using recursion as part of writing programs is probably missing out on a lot of opportunities to write simpler code once you get the knack of writing recursive functions. So, this factorial in maths is actually defined as a recursive function. That's the whole point. Mathematicians will define everything as recursion if they possibly can, because you get this neat little kind of notation turn up where you have a limit over which something happens, and it's... So, in this particular case, 5 factorial is a product of k where k varies from 1 to 5. And you can write that as an iterator or recursive, but you would write it recursive if you're a mathematician to save effort. And that breaks out like that. 5 times 4 times 3 times 2 times 1 is the same as 5 times 4 factorial. And you might notice there's a certain similarity here to the concept of currying. Because currying is really about saving off something so that when you then apply it later with another parameter, you get the answer you're after. And really, that's what recursion is, saving off something so that when you apply it later with another parameter, you get what you want. It's just it's a recursive descent thing going on. So we'll skip part. As I say, this was designed for a workshop, and you never know with workshops whether people are going to pay attention. You always need to have things you can stall on so you can shout at them and say, wake up. So, down here we've got our factorial, and this is our original factorial, defined in terms of a iterator. Defined in terms of a recursion, it's just that, which is a little bit simpler code. And up here we've got our loop for going through and doing our various bits, and obviously this will break on the first instance. It doesn't have the wonderful guard mechanism from earlier. I don't know if I put that in or not. Oh yeah, so this is it with the wonderful guard mechanism added. And just for some fun, right, so all of this up here, we've seen all of this before. I'm now going to get rid of the loop. Because if you come from a language like Ruby, you're used to just saying 5 dot times and giving a list and then going dot each. Well, a loop is just a function. It's a function that knows how to terminate itself if it shouldn't run again. which is interesting. There's a whole bunch of theory around one-use functions and stuff like that. That's quite fascinating if you want to do some crypto stuff. So this stuff sort of ties over to number theory and crypto as well. In this particular case, each is quite easy to implement. I give it a slice and I bury a for loop in it. But alternatively, of course, I can give it a slice and I can actually recursively go through the slice by each time I come into the slice, giving it a slice, but with the first value dropped off that I've already dealt with. So eventually I'll run out of slice and I can check, do I have any work to do? If I don't have any work to do, don't do it. So, which is exactly the same thing, it just looks different. It's mathematically nicer. And so, yeah. All of the rest of that is pretty much the same. It's just now we can say, each parameter, on a panic print an error message, otherwise use the numeric parameter and go off and calculate a factorial and print the answer for me. Oh my God, I think I just wrote a spec. That's kind of naughty. Next thing you know, I'll be writing RSpec in Go. I won't. I really won't. Okay, so the final trick, and I have to pack this one in really quick because I've got fewer seconds than I care for. This is where you can do something really clever. I told you that mathematically a function is a mapping, and that mapping doesn't change. If I give a parameter of 3 and 5 into an add function, the answer will always be 8. And yet I've been showing you code that goes off and keeps recalculating results every time you run it. That's expensive on computational cycles. So I want to calculate the factorial of 10,000, and then I'm going to calculate the factorial of 9,999 afterwards. I'm now going to duplicate calculating the factorial of 9,099 from scratch twice. 3 times, 4 times, 5 times, depending on how many numbers above that I then go off and calculate. And I have a whole chapter of my book about this subject, and the next chapter that I'm going to write on this, once I get bored with writing other stuff I'm working on, is how to distribute this over the network, so the network stores one canonical copy for you. But that code is a nightmare, because it's lots of networking code and database code. But anyway, I can introduce a cache. My cache is just a map between one integer value and another integer value. Boring old hash table. When I calculate my factorial, I first check, have I cached an answer to this question? If I have cached an answer to this question, then I don't need to do any work. If I haven't cached an answer to this question, then obviously I go off and I do all the boring stuff I would do in factorial. Right, so far so good. I've got a global variable that's a cache. We don't like global variables. Somebody's going to come and tamper with my cache. I do not want that to be a writable global variable. Well, we know how to solve that problem. We know several ways of solving that problem. Firstly, I could, of course, just have a private type cache. Right. My cache just happens to be a type of maps ints to ints, and I give it a factorial function. Now, whenever anybody calls factorial on an instance of cache, they're tampering with that cache and no other cache. But of course, this is still a variable that somebody can get at directly, because I'm passing around cache values now, and the cache shouldn't know about factorials anyway. That's not what the cache is for. That's a muddle of concerns. So we'll skip past that. You know, we make a cache, we pass a cache and use a cache down here. Not nice. Right, so instead, I could, of course, make my own factorial function. And my factorial function, any instance of it, can have its own factorial calculator, and it can have its own private cache. And now, whenever you call that instance of factorial, it amends the cache. Nobody else can touch that cache. Only this code path can touch that cache. So now I've got a private cache that will cache all calculations of factorial for me on any one instance of factorial. 99% of the time, if I've got a nice humming system that's been calculating factorials for a few days or weeks, I'm never calculating them again. Now, the trade-off, of course, is memory. And in the old days, when I had 640K to play with and was using hash tables and was driving myself nuts trying to pack things in, it was because in 640K I could not store a lot of data in my hash tables. But in the modern world with gigabytes of data, I'm not quite sure how big the maximum size factorial I could carry in this would be and still have this program do something sane, but it would be a very big number indeed. And it would be storing all the values that have been calculated to get to that point. That's why it's quite a good problem to distribute on the network, so you could have a dedicated factorial server, and then you might not want other people to be able to access it, so that's where you put some crypto in, and you could, there's a whole architecture you can build out of this to show why network caching should work certain ways and not others. Whoop. Now, I was going to show the Y Combinator. We do not have time. What I can say is, buy my book. Don't use any of the code in my GitHub. It's all awful. And I have a whole pile of slide decks, including the very popular virtual machine talk from last year's GoLab, which had almost as many people as this in half the size room. And I look forward to you playing with functions.
Sorry. Can you close it?